So far, we've introduced the electric potential and, for the most part, related it to electric potential energy. Um, Here, I would like to go and relate it to the electric field and get to the real crux of why we like the electric potential in the first place, in that it makes it easy for us, or at least easier for us, to find electric fields. But before we do that, I need to take a brief detour and just insert ways that we can uh, create an electric potential. So, generally speaking, these are going to be batteries, but I think it's best to start with a mechanical battery. Such things actually do exist, and a famous example of one is what's known as a Van de Graaff generator. And if you've been to a science museum and you've seen a thing that had like a big metal mushroom cap on the top, and there was usually like a little conveyor belt thingy stuck in a tube attached to that. And then usually the person doing the demo would get the person in the room who had the absolute longest hair to stand on an insulating stool, put their hands on the mushroom cap, and then you'd see their hair stick out by basically turning their hair into an electroscope. That device is a Van de Graaff generator. I'm just going to look at the nuts and bolts of it, which is literally a conveyor belt. So, the key bit with a Van de Graaff generator is that you'll stick, so let's say it's rotating like this, so the belt's going around like that. It will go ahead and grab electrons, say, over here. So we'll put electrons onto the conveyor belt here. We don't need to get into the details of how that's done, but we'll stick electrons onto the belt here. And so you'll be laying on a pile of electrons. And as the belt moves, what will happen is you go and take the electrons off the belt over here. Now, to just make this a little more concrete, let's say that where we're getting the electrons from is a metal plate there and another metal plate there. Well, as the electrons are being pulled off of this plate and put onto here, that's going to leave behind residual positive charge on the plate there. And since we're sticking electrons onto this plate here, those charges end up over here. Now, the first question to ask yourself is, where the conveyor belt is located, which way is the electric field pointing? Yeah, it's going to be pointing to the right because electric field lines start on positive things and they end on negative things, like so. So that's my electric field right there. And then let me just try to make this a little less cluttered. Yeah, there we go. Oops, lost an electric field line. There we go, something like that. All right, so electrons get pulled off of this plate here. This plate becomes positive. This plate becomes negative. Now, the next question to ask yourself is, as I'm pulling these electrons off the plate and moving them over here, is the conveyor belt doing positive work, negative work, or no work to move those charges? So pause the video and get back with me on that. Yeah, it's doing positive work. And this is because there is an electric force. If I look at, say, any one of these electrons, like let's say that one right there, it's feeling an electric force to the left. Because keep in mind, the electric force is equal to QE. The electric field is pointing to the right, but my charge is negative, and negative right is left. So you end up feeling the electron is feeling a force to the left. So in this case, quite literally, the conveyor belt, I'll just say force conveyor belt, the conveyor belt quite literally is having to exert a force to the right in order to move it, and so the force will be in the direction of the displacement of the charges. That's positive work. But the main thing here to keep in mind is that what the Van de Graaff generator has done, it has moved charges from where they want to be to where they don't want to be. So, they would love to hang out over here by all their positively charged buddies, but instead they're going to be moved over here where there's already a big pile of negative charge, and you're going to be forcing them to join the like charges that they don't want to be hanging out next to. So the conveyor belt has to do work to do that. The same exact thing happens with a battery, and I'll gloss over the details because I'm going to get into batteries more in a later video. But just for our purposes now, I'm just going to make like the world's worst galvanic cell. And I would not recommend trying to make this and actually expect any kind of useful function, but it is technically a galvanic cell. Alright, so let's say I go and stick a zinc electrode into a solution of zinc sulfate. And over here I have a copper electrode that I stick into a solution of copper sulfate. Alright, and then I'll have to connect these together with a salt bridge. Like so. So anyway, the idea is going to be that for chemical reasons, the zinc, some of the zinc ions that are on this electrode here will want to go into solution. So some zinc ions go, that's supposed to be a 2+ there. So some zinc ions will want to go into solution here. And again, for chemical reasons, some copper ions will want to be pulled out of solution here, copper 2+ there. So that's going to have the net result of making this terminal here negative, this terminal here positive. And so again, we're going to be running an electric field. We're going to be creating an electric field between the terminals. There'll also be a field on the outside of the battery. That's what's going to actually ultimately move stuff through an electric circuit. We'll get to that later. Now, very quickly, after a few ions get out of solution, this would all come to a halt because the solution would be positively charged, and trying to pull more positive charges out would be rough. That's why you have the salt bridge here. Let's say it's potassium chloride. Aqueous potassium chloride salt bridge. So what will happen here is some chlorines will work their way in here, and some potassiums will work their way in there. That's a little cluttered. Let's try, say there. So the deal is as, for instance, as the copper comes out of solution, the solution itself becomes negatively charged. So some positively charged potassiums will want to go in its place here. And similarly, as zinc is going into solution, the solution is becoming positively charged, so I'll attract some negatively charged chlorines here. Now, one of the things to pay attention is that we've got 3 different species of positive ions, and they are all flowing in the battery from left to right. And also we have 1 species of negative ion, the chlorine, and it's flowing from right to left. Well, if you think about it though, if I look over here, if I'm moving a positive charge against the electric field, a positive charge would be feeling an electric force to the left. And similarly, our chlorine ions would be feeling an electric force to the right. So again, they're being moved in from where they want to be electrically to where they don't want to be electrically. They're being moved against the electric force. I'll gloss over the details. We'll just say this is F battery, and I won't gloss over the details of how we get that at the moment. But the point here is that just like with the Van de Graaff generator, where kinetic energy in this case was being from rotating the conveyor belt was being used to move electrons from where they electrically wanted to be to where they electrically didn't want to be. Here, it's actually energy being freed up in the chemical reactions occurring within the battery. So the chemical potential energy is being used to provide the energy to do the work to move both the positive charges from where they electrically want to be, the negative side, to where they electrically don't want to be, the positive side, and also the negative ions from where they electrically would like to be, the positive side, to where they electrically don't want to be, the negative side. So this is sources of electric potential go. This is how it's going to happen most often practically. It's going to be as part of an electric circuit. At that time, we'll get into more detail about how exactly the battery interacts with the electric circuit. But now that we know that we can create an electric potential difference, let's go and take a cue from what we see here. What we see here is that the electric field lines are, as I drew them, were roughly uniform anyway. And we know from a daily experience that this would be the positive side of the battery, this would be the negative side of the battery. So if it was a typical alkaline battery versus this monstrosity, this would be at a voltage of plus 1.5 volts. This would be at a voltage of 0 volts. So we're seeing that the electric field lines run from higher voltages to lower voltages. So this is our first step to being able to find electric fields from equipotential surfaces. So let's say I've got some region where I can just draw some equipotential surfaces. Let's say this voltage is higher than that voltage is higher than this voltage. What we'll get is that the electric field lines have to run from high voltage to low voltage. And remember, you do need to keep the plus and minus signs straight here. So this could be 0 volts, and that could be -3. This could be 3, that could be 0. Either way, the field line would run from left to right there. And also, it will always be the case that the electric field line will always be perpendicular to the equipotential surface. And the straightforward reason for that is to say, it's just going to say, let's say that it wasn't. If it wasn't, then that would mean that if I followed along this equipotential surface, I would have some component of voltage of the electric field along this. But then we've seen if I'm following at least even kind of sort of the electric field, I have to have a change in voltage. So therefore it has to be perpendicular. Now, what we can do is it is often easier because voltage is a scalar, and this is really the power of it all. It's often easier to calculate equipotential surfaces. So let's say here, I'm just going to draw in some surfaces like this. Let's say this is 0 volts here. I'll have to come up square there. Let's say this surface is at 50 volts, and then let's say that that surface over there is at 100 volts. First off, I can, at any point, let's say I want to know the electric field right here. First off, I know that at this point right here, the electric field vector has to be perpendicular to this surface, and it has to be pointing from high voltage to low voltage. So I can already work out that this location right here, the electric field has to be running from high to low. But now we can take this one further, and we can also get the magnitude out of it. So we can work out the direction by just looking at the contours and saying it has to run perpendicular. The magnitude will be the change in the voltage over the separation. And by this I mean here, you actually need to look not at the contour you're on, but the surrounding contours. So this would be my D right here. Let's say that at this location it's 2 centimeters. So in this case here, we could say the electric field would be, well, the change in the voltage would be the difference from this contour to that contour. So that would be 100 volts minus 0 volts. And this distance here would be 2 centimeters, which is 0.02 meters. That will give you a 5,000 volt per meter field. Now, on this same contour over here, I can reason that the electric field over here would have to be weaker. And the reason is that because my D here is going to be bigger, just to give it some nice concrete number here, let's say it's 4 centimeters like that. Then here, again, I would have to look at this contour and this contour. You don't want to use this contour because you're interested in how the voltage is changing across this point. And it's better if you can look at both sides of it so that you can say, this is where I came from, this is where I'm going to have a better view of the change right here. So you don't use the contour you're on, you use the flanking contours. But again, it'll still be the same deal. It'll be 100 volts minus 0 volts over, now in this case, we're going to say it's 4 centimeters, so that's 0.04 meters. So that's 2,500 volts per meter there. So what we get is if the spacing of the equipotential surfaces is bigger, the electric field is weaker. So you can look at this already and say, like, if I was looking at this point right here, I can say, well, the spacing is bigger than here, but it's less than here. I know that it's got to run perpendicular to this surface, so it's going to be something like this. And it's got to be longer. This vector here, I have to draw longer than this one because the spacing is closer. I have to draw it shorter than this one because the spacing is bigger than over there. So let's just say, if you were to plunk a ruler down on this and measure it, maybe you get that this is about 2.5 centimeters or something like that. Well, in that case, it's still the same game. You would use this contour and that contour, so 100 volts minus 0 volts, and you would divide here by 0.25 meters, the spacing, to get 4,000 volts per meter. And it turns out that it's often easier to find an electric field this way, where you go ahead and you actually just calculate electric potentials and then use this trick here to find the electric field at a point you're interested in. All right. And we can also go ahead and use this sort of thing to get a more intuitive view of how this works. Or get a more intuitive view for harder to calculate things. We can at least still get a good picture of it. I'll leave that for the next video. Catch you over there.